Hi, welcome to my channel, Math in Local Languages. So our local languages is the Lingala. We have a lot of so many local languages, but the local language that I use for this channel is Lingala. But this time I'm not gonna speak in Lingala because this is an advanced topic, so I cannot teach it in Lingala. It will be a little difficult, but the time will come where we also cover all this topic in Lingala. So this lesson will be held in French. So this is about function in English. Sorry, this is about functional analysis, and we're gonna do some examples, solutions of example on the Beppo or monotone convergence theorem. So we're gonna see monotone convergence theorem, and we're gonna do some example about it. For those who don't know me, my name is Tigana Basel Wenge. I'm a mathematician from the Republic Democratic of Congo, and also I'm studying in Italy at the University of L'Aquila. So now let's get started. So here I'm recalling the statement of the Beppo theorem that's gonna use in our examples. So the statement is that you assume that you are given a sequence of function that you call fn on a measurable set and a measure set, uh, call it capital X, the measure set on which you are given your sequence. And this sequence is a sequence of positive real value function or infinite. And such that these following two conditions are satisfied. The first one is that all the functions of your sequence are measurable functions. For any integer, then fn is a measurable function. The second condition is that for any n, you have that fn is less or equal to fn plus 1. That means that the sequence is a sequence of monotone function, monotonically increasing functions. So then if you have these two conditions and plus the first one that is hidden in the hypothesis given for the function, then necessarily you must find there exists a function f from x to the positive Fourier line that is measurable and that satisfies the fact that these two conditions. First of all, the limit. So the sequence fn converges to f almost everywhere in the set x pointwise. Pointwise means you have this, the limit as n goes to plus infinity of fn of x equal to f of x for almost every x in capital X. That's what it means pointwise almost everywhere. And then you have this, and we also have that the limit as n goes to plus infinity of the integral of fn is equal to integral of f. So this is important. Let us see how we can use this. What is the why is this theorem more like useful in some application. So suppose that we have a sequence of function this that converges to, and our aim is to compute this limit, the limit of this integral. If our aim is to compute the limit of this integral, it may be difficult to compute this limit because of the type of the function fn. And then if we know that all the conditions of the above theorems are satisfied, and we know also our function small f, and we can also see that this function can be easily integrated. So we can integrate it, and then we know that the value of the limit of this integral is just the value that we computed here. But this is not the way that we generally use the Beppo theorem in the other way. That means we will have our function f. So we will have our function f, which will be a function that was given to us, or we found our after modeling some event or phenomenon, and we wanted to integrate this function on a very complicated domain, and this function itself was very complicated, and then we were in a trouble to get the value of this integral. So, and suppose that in some way we were able to build a sequence of functions that are now simple, that we can easily integrate here. So if our function positive, suppose that we have been able to build a sequence of positive functions that we can easily integrate, that converge pointwise to our function, and that is increasing. So we can know, we can directly use this formula to say that, okay, because we wanted this integral will be nothing else that nothing but the limit of those simple integral that we can compute here. Then we can approximate very easily the value of our integral using this formula. So that is the way we use the Beppo-Levi theorem in real life. So because we will most of the time have a continuous function, but which is f, which is difficult to integrate. So we will break. Look, for example, suppose that we have this function. So we can decide to approximate this function like this, like line function on this domain. So if we approximate it like this, you see that these functions that we are gonna build here are just line, so we can easily integrate them. And if in some sense, and we can make this sequence of function converge to our function f, and we can make this sequence of function increasing, so we know for sure that using this theorem that our integral that we want will only be the limit of the simple integral that we can compute easily. So now we're gonna see some examples, pedagogical example, because real example are what we found. Real examples are what we found after modeling things that are usually very complicated. So let us see some pedagogical example. The first example I'm gonna take is a simple example. The first example, I take fn from minus pi to pi to the real line defined by fn of x equal to n plus 1 divided by 2n modulus of sine of x. So we're going to see how to use this to use Beppo-Levi theorem. So the first thing is to check if the function fn are positive, because we must not follow in the real line or or the entire real line, but we must follow the positive real line. So we must check if the function satisfies this condition. So if you look at fn of x for any x and for any n, it is this coefficient n plus 1 divided by 2n, which is a positive number, multiplied by the absolute value of something that is also positive. So this is positive for any x in our capital X, which is minus pi to pi, and for any n in the natural number. So we have the first condition. This is the positivity of our function. We must also check if the sequence of function we have is a measure, the functions that we have are measurable. So if we take fn of x, we can see that it is a constant number that depends on n, multiplied by the absolute value of sine. Sine is a trigonometric function. Trigonometric functions are continuous, and the absolute value is a continuous function here. Then we have a composition of the absolute value and the trigonometric function. So composition of two continuous functions is a continuous function. You multiply by a scalar that doesn't depend on x, or have a continuous function. So this is a continuous function on the interval minus pi to pi. So it is measurable. So fn is measurable. Because any continuous function is measurable. This is for any n. in the set of natural numbers. So the third thing that we must check is the monotonicity. So we must check if fn plus 1 is greater than fn. So we must compute fn plus 1 of x, which is then n plus 2 divided by 2n modulus of sine of x, and we must compare it with n plus 1 divided by 2n. This is 2n plus 2 divided by 2n, and times sine of x, which is fn to c. Then which one is the biggest? So because sine everywhere, we only need to compare the coefficients. So the function that we have the biggest coefficient will be the one that is the biggest. So we compute the difference of the coefficient to see which one is written. So if we get something less than 0 or here or greater than 0 here, then we will conclude that this term is greater than, less than or greater than that. Let us compute it. Then what we're gonna do is we're gonna have 2n times 2n plus 2, which is a positive number. Here we have 2n squared plus 4n. Here we have 2n plus 2 times n plus 1. So what will give us, the denominator will not change because we don't care about the denominator. We know that it is always positive. Let us see what we're gonna get here. It is 2n squared plus 4n minus, this is gonna give us 2n squared plus 4n, and then minus 2. So this is always positive. This is always positive. This is the denominator is always positive. So let's write the denominator is positive. The denominator positive, and this is, they will cancel. This is minus. These cancel each other. So we have minus 2, which is negative. So it means that fn plus 1 is less than fn. So we needed something that will be increasing. So let us change a little bit the formula for fn. So get this to the power minus 1 so as we can have something increasing. So we get it to the power minus 1. So you get it to the power minus 1. Here, so we have it to the power minus 1. The analysis is not going to change too much, but we only change the formula of the function minus 1. So it means that we change the denominator and the numerator for the function that we were given. So here, what we found is that n plus 2 divided by 2n plus 2 is less than n plus 1 divided by 2n. So if we take both sides, take to the power 1 both sides, we will have, so n plus 1 2n minus 1 is less than n plus 2 to the 2n plus 2 minus 1. That will help us with the new way we formulated thing, will help us to conclude that fn is less or equal to fn plus 1. It doesn't matter, it's just an example, so we needed to find the right coefficient so as we have this increasingness of the function. So because of our increasingness, we can use the Beppo-Levi by the Beppo-Levi theorem. We know that the limit, if we take f of x, the limit as n goes to plus infinity of fx, this exists and is measurable, and is measurable, and also if we want the limit as n goes to plus infinity of the integral over x over minus pi to pi of fn of x, it should dx should just be the integral over minus pi to pi of f of x dx. So let us compute f of x and see what f of x will be. So f of x is the limit as n goes to plus infinity of what? Of 2n divided by n plus 1. That is what we will get if we multiply both sides by minus, yes, times sine of x. So if we compute the limit, because this is a constant, we only need to look at the limit here as n goes to plus infinity, which gives us 2 modulus of sine of x. So this is f of x. And then we want then compute the limit as n goes to plus infinity of the integral from minus pi to pi of 2n divided by n plus 1 of modulus of sine of x will only be 2x dx will only be, this is a very simple example, 2 the limit, the integral from minus 1 to pi of sine of x, modulus of sine of x dx. This is a very simple example. And then we can integrate and we see 2 here. It is so you have to give us 4 the integral from 0 to pi of sine of x dx, which is 4 times minus cosine of x from 0 to pi. That will give us 4 times 1 plus 1, which will give us 8. So this is some so you see that it's a pedagogical example because we could already see that when trying to compute when we're trying to compute this limit here, because this is a constant, you can just put it out of the integral and do everything that we did here. But it is more or less how we can also do the same thing with the use of Beppo-Levi convergence theorem. So the next example will be a little fancy, so we will see it in a minute.